Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, I'm sorry if I'm mispronouncing it, Shaharyar, who has completed one of our courses, ROS 2 Basics, in 5 days. And at the end of this project, our student is going to show us what he did for his final project. And in this project, you have to code a behavior on a real robot. So that's what we're going to be seeing today. So hello, Shaharyar, how are you?
Hi, I'm fine. Thank you.
Welcome, welcome. So yes, whenever you want, you can start sharing your screen and just tell us how you've solved your project.
Yeah, okay. I have made a presentation, so I will share my screen first.
Great.
Okay.
Okay, we can see your presentation now.
Can you see the screen?
Yes, we can see your presentation.
Yeah, okay. So, ROS Basics in 5 days, Python. My name is Shaharyar Ahmed Khan Tareen, and I'm a PhD scholar, electrical engineering at University of Houston, Texas, USA. So the robotic tasks were wall following, in which the robot followed the wall, the right-sided wall, while maintaining a approximately constant distance from it. The second task was wall finding and alignment with the wall, and then after wall finding the nearest wall, after finding the nearest wall, it used to start the wall following procedure. And the third task was odometry recording, in which the robot used to record odometry and completes one lap, and after that it stops while following the right wall.
Hmm.
Okay, so the program logic, I divided my program into 4 states. State 0 was basically wall finding. Actually, I will present my project, the last one, which incorporates all the 3 tasks in it, which includes the odometry, the wall finding behavior, as well as the wall following behavior. So state 0 is basically wall finding, in which the robot finds its nearest wall, turns towards it, and moves towards it. The state 1 is wall alignment, which is the same. State 2 is wall following and odometry recording. After aligning with the wall, it maintains a constant distance with it and starts following the right wall while recording the odometry, which is the distance measurement. And state 3 is stop. When the robot completes one complete lap, it stops. So now I will demonstrate my code on the real robot.
All right.
Okay, so here we can see that the robot has started. Please let me just do some changings.
Oh, wow, we're getting a little bit of a crash here.
Oh yeah. Can I reset it?
Yeah, of course, of course.
Okay, just allow me 2 to 3 minutes. So I just reset it.
Do you mean the obstacles?
Yeah, the obstacles
Oh,
and
wait.
the.
I'll actually do that myself. Let me go and run and reset them for you. All right?
Yeah,
We'll
okay.
be
Meanwhile, I
quicker.
can.
In the meantime, put your robot in a correct location and make sure, it doesn't happen. All right, we are back and should be
Yeah,
reset.
just give me a minute. So just let me set the speeds in the code. Yes. Okay. So yeah, can you share the screen?
Yeah, I can see your screen already.
Yeah. So the robot has started finding the wall, which is state 0.
Mm-hmm.
Now it will align with the wall. Here we can see the distance which will be calculated after going in the state 2. After aligning
Nice.
the wall, this is state 1. Now it will start following the wall. Yeah, now the robot is moving smoothly. So we can see the distance is accumulated here.
Nice. Yeah, in the terminal, I can see.
Yeah, yeah, it's very smooth. I tested it many times, so I don't know why it behaved erratically at once.
All right. So it already did the service, it found the wall, and now it is going around the lab, correct?
Exactly, yeah.
Okay. And while it's doing its thing, maybe you can start sort of explaining us how you have achieved this. Uh,
Yeah, the wall following behavior is basically maintaining a distance of minimum distance is 24 centimeters from the right wall, and the maximum distance is 32 centimeters, which I set. So if the starts turning towards the wall, and if it is uh, closer than 22 centimeters towards the wall, it starts turning away from the wall a
hmm.
little bit to keep it, at a specific distance within a slot, within a distance slot from the wall. This is the wall following behavior. And the odometry is basically using the feedback mechanism of the action server, and the distance I am accumulating the distances in a variable called total distance, and I have set a threshold after which the robot will stop
We should
after
be around
completion of
now, no?
almost one. Yeah, yeah,
Nice.
you can see here.
And I can see the
And
robot completed one lap.
yeah,
Awesome.
so
That's great. Very smooth, like you said.
exactly. So coming towards the presentation, okay, so important concepts. Node is basically a fundamental unit in ROS, and a robotic system can have multiple nodes, and the main thing is that we need communication between nodes. So for that we have three communication mechanisms, which are topics, services, and actions. Topics are basically based on publisher subscriber model. A node can publish to a topic, and at the same time another node can subscribe to it to read some values of sensors. And in the same way, services are a bit better communication mechanism than topics. It is based on call and response. And actions are basically also like services, but they can be preempted, and they have feedback mechanism in them. So for complex tasks, actions are preferred. The problems I faced and lessons learned are: problem is that high speed of robot usually makes it unstable, and due to increased momentum, the response time of the robot gets increased at higher speeds. It takes more time to respond, like, for example, more time to stop, or it will drift more or skid more. For good response at high speed, the robot needs higher sampling rate of the sensors like lidar, scan, and other sensors. So the solution is try slower speed for smooth response, like I did in my project. You saw the robot was moving smoothly.
Mm-hmm.
The second problem which I face is that there is a difference between the lidar scan of the simulation and the real robot. Yeah, here we can see that the simulation, for simulation, the perfect right side, the exact right side, if we take the reading of lidar at 270 degrees, it gives a perfect reading of exact 90 degree at right. But for the real robot, it is different. For real robot, if we take reading at 270 degree, it is around almost 45 degrees of in actual of the robot. So so to solve this issue, I used the the lidar scan of 180 degree at 180 degree to get the reading of the right side. Yeah, and the third issue is that if you don't source the code after transitioning from simulation to the real robot and you don't build it, the code doesn't work on the robot. Solution is always build and source the code before launching the launch file. And yeah, these are the two important lines which I found very important. So yeah, that's it.
All right. Yes, I was going to ask you that. Great. So, congratulations. Really nice presentation. Like you said, really nice movement of the robot and quick and easy explanation. So, I have some questions if you don't mind. Um, so, can you hear me?
Yeah, thank you.
All right, cool.
Yes.
So, my first question is related to what we saw in the first try. So, we saw the robot, crash against the obstacles, and then you went in
Yeah.
and changed some things.
Yeah.
What was the reason for this crash? What were you testing, or?
Yeah. Yeah. I actually tested the robot 2 hours before. It
Uh,
was moving smoothly. So when I just connected with you and started running my project, my code as a testing now at that time, so the robot's behavior was erratic. It was moving. It wasn't moving smoothly. So I what I did was I increased the speed. So due to that increase in speed, when I again built my code and launched it, you saw the behavior that it
oh, so
came
the,
out.
the
It
the
went
speed
out of
was too
control.
high, and then
Yeah,
maybe
exactly.
okay.
Yeah,
So what we saw was sort of like it was looking for the minimum value of, and it overshot
yeah,
it or something.
yeah. Yeah, it overshot the sampling. The sampling rate of the sensors was not compatible with the speed of the robot. The speed was too high, and the rate at which the lidar was reading the sensing the environment was slow,
The
was less.
rate at which the lidar arrives to your ROS check, I think it's between 4 and 7 hertz. Is that correct?
Yeah, I am not sure, but yeah, I think so.
You can check it just to remind you. You can check it with ROS2 topic hertz and the name of the topic, and you can get a precise number of that. And then you can figure out at what frequency you have to spin your node. You probably have a spin once or a spin function of the
Yeah,
RLC pi function that creates that. So maybe that's the mismatch. But I was thinking maybe there was an obstacle closer to the robot than the actual wall.
yeah.
Maybe that
No,
was an issue, no?
no, not obstacle. It was because of high speed.
So what happens if the your program is launched with an obstacle that is too closer than the
Actually, yeah,
wall?
yeah. I am not taking one reading in one direction only. I am taking reading in multiple directions. Like, for example, you can say
So
that reading in three different beams.
right. So when you launch the program, it would detect the minimum distance, and if the minimum distance is the obstacle, it would go towards it?
No, no, it won't go. It will check some other beams as well in the same direction, but with some increment, and find and check that whether the whether the range of those beams are also compatible with the wall or not. Because if there will be an obstacle, the range for those extra beams won't be near the minimum value as compared to the beams
Right.
for
You
which
will
the
have a
obstacle was
smaller
detected.
cluster of
Exactly.
similar length
Yeah. So that helps
values.
to detect the wall.
Oh, nice. So there you added an extra thing, a little little extra filter that prevents
Exactly.
you running into the robot. All right,
Yeah.
and this frequency and spin of your node, it further confirms what you said about it moving slowly. Maybe that was like a mismatch of frequency. Yeah, it was going pretty fast already. I mean,
Yeah.
it's a small robot. It can't. So I can imagine that if you force a really high speed, that might happen. And another question I had is how do you determine that a lab is completed?
Yeah. I am calculating the distance,
Mm-hmm.
and I am accumulating the values in a variable. I set a global variable called total distance. And when I was testing the robot, I tested it more than 20 times.
Mm-hmm.
So when I was testing it,
As you should.
I calculated the robot's distance for one lap multiple times.
Yeah,
So
nice.
I set the threshold value for that distance, and when it reached that threshold, I just stopped the.
Nice. All right. Well, very nice. Again, very nice behavior. I really like. Oh, and one comment about first, I really like that you use the packages only flag to compile only the packages you need. Very nice practice. And you mentioned an issue that, I'm sorry, are you, says your bandwidth
Yeah.
is low. Are
Sorry, I
you
wasn't able
around?
to hear you. Yeah. Yeah. Can you repeat?
Yes. So you commented that you have to compile and source in the real robot, but not in the simulation.
No, no, no. We have to compile and source every time we change our program.
Yes, yes. And the reason for this, even if it's Python, is because the Python ROS2 libraries are basically bindings to a C++ library. So that is why you need to recompile every time you change, even a configuration file, if you have one, in ROS2 in order to reflect those changes. You can make changes, you can go a little extra work and go around it, so you don't have to do that. But by default, yes, you do. You do have to. Um, but yeah, other than that, I really liked your project. So congratulations again one more time.
Thank you.
All
Thank
right.
you so much.
Yeah, and that is it for all of us. So let me change my screen here. So yes, whoever else, for all our audience that is watching, this is what you can do after you finish certain of our online courses to obtain a certificate, improve, and certificate that you have taken something out of our courses. So I encourage everyone to do the same and to keep pushing your ROS learning. Thank you, Shaharyar, and we'll see you again for next time. Bye bye. All right, it's done.